So today we have Michele who's going to tell us about examples of GPU programming.
Thank you. So, the title's here. So this is the outline of the talk. I mean, there's a lot of stuff because it's basically this is sort of a retrospective of all the technologies that I've ever touched in my programming life. So I will talk a bit about CUDA, about OpenCL, not that much. More about OpenACC because that's something I've been working with more. I will talk also about, I will show also the profiler, the NVIDIA profiler, because I think it's a nice piece of technology which is quite easy to use and worth mentioning. And I'll also talk about a bit about OpenGL. It's just some hands-on, some tests, some attempts of making a small OpenGL program that will work that I did like 1 year ago, which works half. Disclaimers. So I have only experience with the NVIDIA GPUs. I know that there's some part of the world where people tend to use AMD cards. For example, in Germany, I know that there are groups which are really into this. I have little experience with OpenCL and CUDA because I've never actually written real code for this with these technologies. I had to configure some problems using them. Not really. Yes, and I have written some real code only with OpenACC. I don't consider myself an expert. I can say though that I've been using OpenACC for some years, and we were using the PGI compiler, which is the only one at the time, which was the only one which was supporting the OpenACC standard, and I managed to find some bugs in the PGI compiler. So this is my my point of pride. Yes, my experience with OpenGL is just related to a small personal project to satisfy some queries. So let's move on. So I had a glance at the video of the last meeting where Jarno was describing GPU computing as a whole, and so I won't go through these things again, but just to point out some important aspects. So GPUs are a heap of very simple computing units. I don't know if they can be called slim cores, maybe not even slim cores. I think that would be KNL is just a heap of slim cores. When programming for GPUs, one has to mind and remember to move data when it's necessary, and also try to move data the least possible, just when it's come to with it. And also, one thing that people tend to be paranoid about is branches. We'll see maybe what is the problem with this. And also, the problem of usually porting application to GPUs that the memory layout that is needed to get good performance is usually different from the one that you would have on a CPU. Things are possibly converging in the future because of the vector length on CPUs, which is increasing. Now we have IVX 512 instructions, which require similar approaches to structural arrays memory layouts. I could just say that for us on GPUs, we have seen that structural arrays, this kind of layout works best. The other option would be the array of structures, which is not recommended anymore in GPUs, except for some things where actually it works. An exception is actually graphic programming. In graphic programming, usually people have float 4. And they use these small vectors to represent a vector, and they don't need to have more complicated memory layouts. On KNL, on other architecture, people are supposed to use or are encouraged to use a more complex data memory layout, which is an array of structured arrays. But for what I've seen and for what my collaborators have seen, the structural array is the safest and the easiest solution. Okay, so I'll talk a bit about CUDA. I told you I'm not an expert, but the fact that OpenACC is really heavily involved with CUDA in some sense, at least in the way I have experienced it. So yeah, I got some. So as you know, there's the need to move data between the device and the host, and you can do this with asynchronous or synchronous memory copies. Okay, that's something to take into consideration sometimes. There's a way to manage asynchronous kernels. This is somehow recent. I mean, possibly the first iteration of CUDA didn't have this feature, but now it's possible to do this. And this feature is also filtering. I mean, it's also possible to use this in OpenACC. There's also the possibility of launching kernels from kernels. It's not only that you need to launch kernels on the GPU from the host. This is a sort of a newish feature of CUDA. In the early version it was not possible. They also added a feature which is called GPU Direct, which allows to move data more efficiently between devices. And by device I mean GPUs, different GPUs, but also GPUs and network card, for example. There's also the possibility of having unified memory management, so that basically you don't have to specify manually that you want to move the data. We have never used it. We did a benchmark with that, and actually it was not so good. So actually we prefer to stick to the manual explicit data. There's also a GDB extension for CUDA. I've never used it. I learned to use debuggers 1 year ago, more or less. And also there's a quite nice piece of software, which is the NVIDIA Visual Profiler. It doesn't work only with CUDA, it works also with OpenACC. It works on NVIDIA cards, basically. The documentation is really good. I usually find it really interesting. I always find something that I don't know when I read it. Every time I go there. So let's move on. Some other information about CUDA. So, about the execution model, there's the host code, which is usually written in C and C++. I'm experienced with C usually. And from the host code, we can invoke some device code, which is usually denoted as kernels. We have threads. I mean, the kernels, the unit of work that the kernel does, that all the kernels does, is divided basically in threads, which are grouped into blocks. And these blocks can be organized in 1-dimensional, 2-dimensional, 3-dimensional grids. Personally, I've always used just 1-dimensional grids, but I guess that, I think that there can be an advantage in using higher dimensional grids and setups, because this can actually help with data reuse, especially if you have some sort of a lattice kind of lattice or a 2-dimensional or 3-dimensional domain that you need to process and so on. One very important thing to mind is that this is more a thing of the device, so of the NVIDIA cards. But they use this SIMT architecture, so it's single instruction, multiple threads architecture. Basically, all threads actually doing the same, doing the same thing. So they have the same, executing the same instruction. So it's a bit different from the SIMD, with the which is the typical vectorization scheme. Yeah. Yes, I think it's clear the difference. And yeah, and there's on currently on the threads are grouped in warps, which are groups of 32 threads, which must execute at the same time the same instruction at the same time. So if you have an if statement and there's a branch in your code, what will happen is that basically this split, there will be what will happen is called a warp divergence, and basically some of the threads will be stopped, and some of the threads instead will keep going. So this is not such a big deal usually, but well, one could mind this. It's possibly quite easy to work to find workarounds. Another thing that must be taken, another important thing to mind when you code for GPU and CUDA is that, well, there's a memory hierarchy. So the host memory is the one that you want to touch the least possible. Then there's the called global memory. Global memory stays on the device, okay? And it's usually up to 10 gigabytes or so. I think that I've seen cards with up to 24 gigabytes. Maybe this has increased recently. I don't know. And while the bandwidth to host memory is around tens of gigabytes per second, the bandwidth to global memory has increased quite a lot, because I think that NVIDIA has realized that there's need for higher memory bandwidth with the global memory. And it's around, in recent models, it's around, possibly in the order of 1 terabyte per second. Yes. The cards that I'm going to work with today, I think that it's around 200 gigabytes per second. But anyway, not only, but bandwidth is not so, the only thing that's important. There's also latency. Every time you go to get something in global memory, it's, if I remember correctly, it's like 500 clock cycles, which is significant. So, shared memory, basically, I think that, shared memory is a logical thing. It's a logical concept. It's actually the memory that can be shared between threads in the same block, okay? And I think that it's related to cache. In recent-ish GPUs, there are also cache levels, level 1, level 2. And then there are also registers, which are private to threads. And there are also some other features to mind, to think of, which are some other kind of memory. So the texture and constant cache, which are read-only. And I've never used them myself, but people tend, using texture memory can actually give some performance advantage. I think in some cases, it's small, but it's there, like 5% or so. This is what we saw. So actually, but it's it's quite more complicated to use text memory. And if you want to somehow speed up a bit the transfer between the host memory and the global memory, you can use memory pinning, which is basically a way to avoid the swapping. Basically, when you pin some memory on the host, you make sure that this memory is not moved anywhere. So it stays there, and so it's faster to transfer to do the transfer with the GPU. Okay. Other things. So I'm moving to OpenCL now, and eventually we will go to the example. So I don't know very much about OpenCL because I've been working mostly with NVIDIA GPUs. And NVIDIA GPUs support in some sense OpenCL, but only up to version 1.1. And the most striking thing is that in version 1.1 there is no double precision support, okay? Except with extensions. So in 1.1, if you want to have extension, you need to load if you want to have double precision arithmetics, you need to load some extension, which depends on the accelerator you want to work with. The most recent version of OpenCL is actually 2.2, okay? And I think that there's a quite big difference between 1.1 and 2.2. But well, it seems that NVIDIA is quite invested in other technologies now, so this possibly explains this. So there are some concepts which are similar to CUDA. For example, the thread blocking. They are not called thread blocks; they're called work group, I think. And yeah, they can be 1 or 2 or 3 dimensional. And it's a bit. I mean, the way the program behaves is a bit different because basically the kernel code, the code that will run on GPU, is not compiled before. It's compiled at runtime. So there's some host logic that takes the program and compiles it. This is the way, the only way they sought to achieve portability, actually. So the fact that then it means that in the program you need to take care of all the possible devices that you will ever encounter, and you will also be able to decide if you want to use this version of the kernel with this hardware or not. I mean, so it's a bit painful to configure in my experience, and on HPC Wells it was not configured correctly. Found out. But I think we can move on. And then that's what I know more, which is OpenACC, which is very similar to OpenMP. It's the same spirit, basically. It's a declarative way of programming instead of prescriptive. Basically, I mean, everybody knows what OpenMP is, I think. So. And there are similar concepts to CUDA because, well, eventually, well, I mean, for example, if you want to run OpenACC code on NVIDIA cards, under the hood, what happens is that the NVIDIA compiler is called, and then NVIDIA specific code is generated. And well, there are also some other reasons why it's so similar to CUDA. But I think that there are some similar concepts even that are shared with the OpenCL, which possibly can be. So there are some things which are common to, and so it means that it makes sense to have this kind of, for example, the thread blocking, etc. So in an OpenACC program, you tend to specify the way you want to you want your code to be parallelized, and there are similar concepts. So the similarity is really clear. So you have gangs of threads we can share work, okay, which are basically analogous to the thread blocks in CUDA. Okay? And inside each of these gangs, you have workers, which are basically threads, okay? And so can share data, okay? And then you have a third level of parallelism, which is not explicit in CUDA, or maybe it's just it has no name in CUDA, but which is the vector level, which is the SIMD parallelism. And with the addition you have with respect to OpenMP is that you need to manage explicitly data movement between the devices, between the host and the device. Yeah. And there are also some features which are called data regions, which make this a bit easier to manage, so that you don't have to be too explicit with it. I will show you the examples. So usually I don't know if you know that there is a picture from XKCD, okay, about competing standards. Like there are 14 competing standards, and then there's a guy and a girl saying, "Oh, we actually need to create something that will encompass all of them, and then after this there are 15 completely standards. Sorry, it would have been better to put the comic here, but anyway, you can imagine this. Yeah, so the fact is that OpenCL was born before OpenACC, and the idea was that it would work on all the possible devices that you could think of. And actually it does, it's just that it's a bit hard, cumbersome to configure and cumbersome to use. I will show you an example, an official example, taken from the official repo from MED, which is quite complicated, and I will show you. So I think that people with OpenACC wanted to come up with something which was somehow simpler to yes. I mean, you cannot achieve exactly the same performance with OpenACC that you can achieve with OpenCL, because OpenCL is a bit more specific, you have more knobs that you can actually tune. And here in OpenCL things are actually delegated more to the compiler and to some logic that the hardware vendor should take care of. Yeah. So the problem with this, where I'm going with this, is that basically it's supported basically only by the PGI compiler. Actually, there are other attempts. For example, GCC has also a branch that supports OpenACC, but I think it's the performance you get from that. It's not so great. So we tend not to use it because, well, I mean, the reason why you go to GPU is to get performance. If you don't get performance, and also, as you possibly have already read, NVIDIA bought PGI some years ago. So as a result, we have the OpenACC works very well on NVIDIA cards to the same level of CUDA, I think, for some things, for simple kernels at least. But for AMD ones, our experience is that actually doesn't work so well. One thing to say, I mean, I know that, well, I didn't study too well, that OpenACC is a new standard, but in fact, OpenACC can be seen as the idea of an OpenMP extended to accelerators. So in the future, and yeah, this is somehow happening, basically OpenMP will possibly just be, I mean, if you write a program in using OpenACC, it would be possibly quite soon, you will be able to just replace the OpenACC pragmas with OpenMP, okay, without changing the code, and get the same level of performance. Yeah. So still, I think that OpenMP it depends on the compiler. CLang, for example, has some good level of support. GCC not too much. When we talk about OpenMP, Cray has good support. But anyway, we can actually look at this presentation if you want. It was last year presentation. So well, I mean, now I want also to talk about OpenGL because I think it's interesting, and for me, having coded on GPUs for some years without actually having ever done any graphic programming was a bit puzzling, a bit strange. So I decided to learn a bit of this. For some things, it's quite similar to OpenCL. Possibly it's because it's a standard which was produced by the same institution, which is the Kronos group. Yeah, so there's a host code, which is basically a state machine where you choose which program you want to act on, which buffer you want to act on, and then you do some operation, then you change the buffer you're acting on, and then you call some other operation. We will see that. And yeah, I think that possibly the GPU part is made, which is the interesting part for us, I think, is made of basically of programs which are called shader programs. You can have many shader programs in the same host program, okay? They are compiled and linked at the runtime of the host program. Okay, and they are quite simple in this. I think there's a flow. There's a pipeline. Okay, where basically the execution goes through. So you have your data is first. I mean the data of the mesh or the geometric data of your models is first processed with the vertex shading. Then there are some steps which are optional now, which is the tessellation. I think you mentioned that on the last talk, where you basically create a new geometry. Okay, like if you need to add some points. For example, the idea is that if you have a sphere, you could actually have like a very limited number of points in the sphere. Okay, and then you add some more points on it, so that your model becomes better looking. Okay. There's some additional processing in geometry shading, which I don't know exactly what it does. Okay, the solution is somehow clear to me. Then there's another step which is actually done automatically by OpenGL, and then there's the so-called fragment shading, which is basically when the GPUs computes the color of pixel on the screen, basically. This is an OpenGL jargon, because if you go to the Windows to Microsoft, I think they call it this part they call it pixel shading step. Okay, and then there are other operations that are done later, which are like testing that decide, for example, if a pixel must be shown or not. For example, the depth testing. For example, if you have something behind another, you need to show only the first one, which means that actually all this step will be repeated. I know I will be retrashed because you have some show. And also stencil, if you have, for example, well, you know what a stencil is. It's an English word. So if you have some area which is not visible because it's outside of the stencil, then that thing would be. I don't know if actually this operation could be also done before, but yes. Anyway, let's see some examples now. Okay. Any questions? Any comments? Any? Not so far? Okay. So, there are some things. So there are basically 5 topics, and so I will go through them and show this. Okay, let's go to the. Yes, I'll show you first the CUDA example, which is actually on this machine. Okay, so this is a very simple one. The OpenACC example, which will be much more complex because it would be a real code. So here we have this function which is defined as global, and global means basically that tag over there means that this is a function that would be executed as a kernel on the device. Okay, and you can see that there are some built-in variables, which are this block IDX and locked in and thread IDX. Okay, which will be fed automatically to this function. Okay, by CUDA. Okay, and they're basically, they have no mean, they are not related to any address in memory, for example. They are just some counters that we can use to as we please. Okay, and but we know that, for example, we have a different thread IDX for each thread running. Okay. Yeah. So here it's evident what we're doing. We are just summing two arrays, okay, in a very SIMD fashion. I can say.
Those block IDs and thread IDs, they are defined by the compiler when you.
Yes. Yeah. As you see, there's no definition of this in the code. Yes. So basically, this thread IDX, the thread index. Okay. As you see, there's actually it could have more than. I mean, it has .x, but it could be also .y and .z.
Yes.
Yeah. Yes. And it's defined by the compiler. Yes. And this is the thread ID. There's also the block ID. Okay. Well, I think it's quite clear. A block of threads have yes. And one thing to notice is that here, yes, this I could actually be larger than n. So now we are working, of course, on some arrays which are size n. Okay. We need to specify n because for obvious reasons. But I could be larger here, so we need to have this if there. Okay. So well, it's not a problem because just there will be some threads we will be doing nothing in the last warp would be diverging, but well there's no other branch, so basically we are not doing it. But we need to have this if there. Okay. Okay. And well, so here you see that we are allocating stuff on the host. We need to set the device. I don't know actually if I would be able to use this device. I need to check if this device is free. Anyway, I will check this later. And then we also want to allocate some stuff on the device. We fill in the stuff on the host. We copy from the host to the device, okay, and then we can finally call our kernel with this strange notation. So basically, the first number here, okay, which is a single number, just because we are using one-dimensional blocks, sort of, okay, and this tells me how many blocks I want to have. Basically, it would be the maximum of those .x, that's one. And then this is instead the number of threads I want per block, okay? And then I call it as a function. So basically, between the name of the function and the argument, I need to put this triple lesser and triple greater signs, just to say how I want to call the things on that. Yeah. Then I need to synchronize. It's not. I don't know exactly if I need to do this. In some examples, they say you need to synchronize. In other cases, no. But yeah, it could be that actually this kernel is launched on a different stream that, for example, this memcopy. Okay. So this is non-blocking. This call happens, but basically, well, we still don't have the results. So well, basically, I need to synchronize here and to make so that this call happens after this. The difference here, well, I'll see that there's the argument has switched, and here this variable is different. And yeah, so here we just have some host logic which checks what happened, and eventually we free. We free on the device and on the host. It's quite important to free the device things on the device because we don't have too much memory there. Okay. Actually, memory on the device can be a problem, and that's why, for example, sometimes it's necessary to go on multiple GPUs. It's not something that you would like to do in general because it's good. It's just that it's necessary because of memory problems. And okay, then okay. So let's see if we can run this. Okay. I need to. Now this CUDA 7 is actually possibly 2 years old. but yeah, I mean, but it works. I mean, if I use CUDA 8, for example, here, possibly this model is misconfigured and it doesn't. Anyway, so we load the module and we compile. Maybe. Okay. So, and VCC is the compiler by NVIDIA. We specify the architecture here, and well, that's yes, that's it. So the syntax is really simple. Okay. Just to see if you remember, I actually said that I specified in the code. I specified the card I want to run on. I need to see if that's free or not. Is this, yeah, because I need actually to go on the device, on the machine here. So okay. Okay. Nothing is running there. Very good. So actually can run it. Yes, I'm not particularly good, but one thing I can actually do is to profile it. Okay, I think okay. Yes, there's also I think an opportunity to see the results. Okay. But this is a very simple program. But you can see that, I mean, these are the functions that have been called. So you see that actually moving the data from the device and between the device and the host takes a lot of time, much more than running the actual kernel. But this is a very stupid kernel. You would like to have actually either, I mean, there are two options. Either you have a bigger kernel, which is quite good idea, because actually every time you launch a kernel, you pay some latency. Okay? Or maybe you can actually just call more kernels, but without having moving the data.
Sorry, do you remember how big an N you had for this?
1 million.
That's 3%.
But anyway, I think that this thing will be scaling. I mean, if I take 1 million here, it will be the same, I would say, because anyway, yeah, it's really. I mean, arithmetics is quite simple here, because usually you have the ratio between the bandwidth host to device and the bandwidth between the global memory of the device and the computing unit in the device itself, which somehow, because this kernel here is going to be definitely memory bound, because it's really simple. It has a very low arithmetic intensity, and yeah, you can see here. I think that, I mean, the copy host to device. It's larger because we need to copy 2 arrays instead when you copy back to copy just 1 array. So we see that actually this really matches. Okay. So well, this was a very simple example of CUDA code. I have other examples. If you want, we can look at them. But let's see what happened with, I mean, I can show you the result of the profiling, which is really boring, but anyway. So there's this NVIDIA visual profiling, which is quite good. Actually, I can show you a bit nicer thing, because this is profiling data of another program, which is a bit richer. Okay. But this program was actually written in OpenACC. So So here we have timeline, and we have some copies. You can actually see yeah, these are copies, but we have also the compute. Yes, and you can see all the kernel launches. Yes, and you can see the grid size, the block size. And yeah, this is a different example. I can show you the code for this, but this code was written in OpenACC, which possibly is a good hook to go to the second example, which is OpenACC. Okay.
Quick question. What is every row there?
So every row is here. It's a. I show you if I manage to. Okay. So this is a kernel basically, which is an OpenACC function, okay? And yeah, so they are. Yes, and it's true that they can be executed in parallel. Some of them will be possibly. For example, this profiler is a good way to say to see if there is. If your code is executed in the way that you expect it when you use asynchronous kernels, for example. Also to see the transfer, the data transfer is quite good, I think.
So each one of those colored blocks could be executed in multiple, let's call them cores. Is that right? Yeah. It's a kernel launch, but not necessarily. But
yeah,
it
it's
doesn't correspond in any way to the number of executions of that kernel. It's just one per multiple execution.
Yes, for each invocation.
Yes.
Yes, so yeah, you should have like 10, because this is just a profiling run to see how it works, how this code performs, and yeah, so it's okay. Well, I'll show you the code, which is an OpenACC code. If I don't touch, so it's this is just there's a lot of so there's a lot of logic here that we don't care about, which makes this this file quite boring. Sorry, because okay. So there are some OpenACC directive here, and you see that So this is so here we want to with this function we have produced some data which is it's a global variable. Sorry. Okay, and actually it's a two-dimensional array, and basically what we do is that we copy that on the device. Okay, so this is a way to manage copying data from the device to yours, etc. In this code, we actually use a lot of this, which we use this method to manage data, which is just we explicitly say in the point in the program we want to copy this to the device, and we want to copy it back, or we want to update, for example. For example, this update. So we have already created that on the device, but we want to update. Sorry, possibly this is not the best, but I think that this program was written when I didn't care too much about the shape of this, but more into I had no time to think about how to do things.
So these part also are similar to this. The memory copying, the
exactly.
CUDA, right?
Exactly. Instead, yes. The cool thing is that if you run this code, if you compile this with the GCC, it can actually, or any program, any compiler that doesn't recognize these pragmas, you have perfectly legal code. So actually, in developing this, when I was developing this, I was usually first of all compiling this with GCC, and then adding the pragmas and using the PGI compiler and try to see if things go sensible. Okay, so this is the main logic. Okay, but I will show you the actually the logic of. So, for example, this is the function that we are actually trying to study. Okay, and I'll show you how it looks like. Let's see. Okay. So basically, apart from some stuff, here we have, yes, so here I'm stating, okay, that the following code is going to be executed on the device in a parallel fashion, okay, and here I specify that all these symbols or all these variables are present already on the device, okay. If they are not present, I need to specify. I can specify copy in or copy out or just copy, which means that it will be copied both in and out, okay. And here I can specify, for example, that this loop, the loop that just follows, is made of independent iterations, and it can be split into different gangs. Okay, so that's yeah, and the following three loops actually are I mean they are described as a tile basically. So I mean we are telling the OpenACC. We're telling OpenACC that they can be split into tiles. Okay, this will be a three-dimensional tile. In that way. So basically, I think that all these parameters here, I think that they should be like equal to 8, all of them. Okay, even this one. Okay. Yes, and actually the dimension of these lattices are around like these should be 8. And you can actually see that this 8 and these are, sorry, this yes, this D3 or locking 3, this is actually 8, and this is actually 32. So I think it should be possible to see that in here. Sorry. I mean, you can't see this here because it's something that is specific to the kernel. You can see that there is, yes. So the grid and the blocks are split in this way. This is something that the compiler has done on his own. I specified this, and the compiler has produced some CUDA code under the hood, which was then, which when it was ran with that in that configuration. Yeah. So I defined some macros here just to make the code a bit more concise. I find it a bit strange. I mean, I never managed to. I think it's impossible to use pragmas inside macros. I tried once, but I haven't managed. Yeah, and there are also some strange instructions here, I think. Also here, and well, basically, the reason why we have this is quite simple. Basically, we are on a lattice which has periodic boundary conditions. Okay, so if you are close to the boundary, okay, in order to get the neighbor, okay, we actually need to do you know, to get. I mean, if you are at the right edge, we need to get that to and this is some logic which usually, I mean, would require some sort of branching. Yeah. Instead of branching, we use this, which is, I mean, yeah. So if we write the data in Visual, we don't have branches. I don't think that they would be such a great problem for us. This coding is anyway heavily memory bound, so memory bounded. So, but you know, just to be extremely cautious about branches, we use this kind of. So yeah, we basically do the. Yeah, I don't know. I think that it's. I mean, it puzzled me the first time I saw it. If you want, we can discuss it.
Okay. And now the benchmark calls some other functions like this, so that's why you have all these, yes, all these kernels. Yeah, and that's it, I would say.
Questions? Any comments? Something? Puzzle?
If not, I move on. Okay. I need to find the OpenCL example. It's here. Huh, yes, it's here. It was not so stupid. So, okay. So, just to have a. So actually, this is as you may understand. Actually, this kernel. This is very simple example of a kernel which just does matrix transposition. Okay, and yeah. So this is the kernel. So this is what actually the code that runs on the GPU. Okay, but then there's a lot of work that must be done in order to check all the errors and yeah, which is yes, I mean it's really significant to me. I don't know if in practice people do always write this kind of things. Maybe not. This is possible. This is an example by AMD. So I suspect that they want to do everything by the book, but yes, and so yeah, I think that it could be interesting to see the logic that is behind running the kernels. Okay, so basically, I think that it's they create a common queue here, sorry, which is and items of work are added to that. Okay, and then eventually, yeah. So we wait for. So here, for example, you see that we actually add a kernel. I think. And yeah, I mean, this is the second time I look at this example. So. But yeah. Yeah, I'm. Think that eventually there's yes.
I think that well, we add stuff to this queue in some sense, and then we, I think we just call it. But I don't know. Call this finish just to wait for the completion of it. Yeah. Quite interesting. Unfortunately, I had no time to look into this. And well, the problem for me is that I always work with NVIDIA GPUs.
I mean, actually, on this laptop, I have
a Radeon graphic card. So, and also, well, OpenCL is supposed to work also on other kind of devices, for example, FPGAs, but also Intel graphics. But well, for heavy computing, I think that I don't see any possibility that we will use OpenCL because we are working with NVIDIA GPUs. If you don't have any questions on this, anyway, I don't know if I can answer them, so maybe I can move on. Yes. Okay. Sorry. Now I remember. Okay. Let's see if it works. Yes, doesn't work. Okay, perfect. Okay. Yeah. Yes, because I need to do this. And then, yeah. Now, the problem with the graphic programming, as far as I understand it, is that okay, you can try to write your own kernel, your shaders, etc. But then there's a lot of things that must happen before you do that, which is managing the OpenGL context, all the stuff that you like to, because there's of course, if you want to have some sort of interactive visualization. So maybe now it will work, or maybe not. Okay, so this is exactly what happens usually when compilation of shaders fails. Let's see if I quit. Wait a moment. Okay, so yeah. Yes. Okay, I will try to show you something that works, but this is the kind of examples, I mean, just an example of things that can go wrong, which was on purpose, actually. Believe it or not. Actually, it should be working now. Interesting. So let's read it. Sorry. Okay, but maybe we can actually look at the code then. So there's some C++ logic here, which is just doing some. So we create shaders, and in order to create shaders are actually, these shader objects represent shader programs. Okay, shader programs are defined in this way. Okay, and yeah. So for example, we need to load the shaders, which are basically just files. Okay, I can show you one of them. Okay, so this is what will run on the GPU. This is a fragment shader, so it's the last piece of program that will be executed actually, which defines the color of it. So yeah, one thing I want you to notice is that actually I have some version of shaders because they, for example, this shader here requires version 1.2 of the OpenGL, of the GLSL programming language, which is this programming language, which is actually a subset of C99, this one. But there's also, I had a working version of, wait a moment, so there should be actually, why is it not there? Sorry. It's only the basic shader.
this is quite unexpected. Sorry. Sorry, of course, because it's not checked out. It's a promising name.
We editing this one. Yeah.
Git checkout not working nicely. Can you find more?
Yeah. So actually, yes. So these are just the two shaders that you need to have in any shader program. Okay, which is the yeah. So these are the same thing. Okay. There should be there are two. So sorry, one is the vertex shader, and then there's the fragment shader. Okay, and they are linked to. They are compiled and linked together in this shader object. I think that here it's possible to notice that, for example, this is the fragment shader, so it's the last one. Okay, the first one is shader.vertex, yeah? And yeah, so we specify here, for example, that we have some uniforms which are basically constant quantities, okay, that will be used in all the by all the kernels running, by all in all the runs of the kernel. Okay, these attributes actually are quantities which are defined in the main program, okay, and defined to some attribute of, for example, the mesh, or so these are actually vertex attributes, okay, and yeah. And then we have some outputs of this shader, which are this thing. So these are just the three-dimensional vectors. And here it would have been a cool example because there was the normal, but there was also the position of the light. Because there were, I wanted to show two cubes with the light going around. So, but yeah, this worked like 1 year ago. But then what happened is that I needed to change everything in my laptop because I wanted to have the OpenCL, some OpenCL code working, okay, and I need to mess up badly with my my drivers, and now it's like this. Yeah. So this is the vertex shader, which is quite simple, okay. Yeah. Yeah. There's some geometry here. For example, this is a 4x4 matrix, which multiplies this back 4, and this is the way that actually OpenGL manages moving the camera around. Okay, so there's this is a matrix that basically defines the camera position and orientation. It's an acronym that stands for Model View Projection. I think. Yes. I don't remember. Yeah. But this is a mathematical course. And yeah, so I think that you can see that what is outputted by this vertex shader program is then taken as input by this fragment shader. And that's it. And that there is some logic there to define eventually what is the color of each fragment in the scene. Fortunately, it doesn't work, but well. Yes. The syntax is really dependent on the version. I mean, now this is one of the latest versions. I think that now there's 4.8. I think that the latest version of OpenGL is 4.8. So 4.2 is quite modern. In the other versions, the other shaders were based on a much earlier version of OpenGL. And actually, I think that the OpenGL
programming style has changed a lot. I think that what is after OpenGL 3 can be considered modern, and before that it was pretty, the way of doing things was quite different. Anyway,
Before that, it was just standard C program, right?
yeah, I think yes. I mean, there were no.
There were no, all this fancy stuff was not there.
Yeah. Oh, yeah. I think I showed you more or less what I wanted. Not didn't work. This example didn't work. But anyway, hope that was somehow interesting. So thank you for your attention.